comments, questions. This is your time. First 5 minutes, your time.
Doctor?
Yes.
You deleted the homework assignment from the Blackboard.
No, I didn't. I'll check right after class and see. I'll make sure it's there. No, I didn't delete it. How come it's deleted? Okay, what else? Let me check it as we speak. Did the due date pass of the homework assignment? No, it's not. It should be there. It will be removed after the deadline. Due date of this homework is Monday, the 2nd of November. Let's see the why it's hidden. Gotcha. Okay. So, yes. November 2nd. Now it's there. Okay. Now it's there. Now it's there. I don't know. I put an incorrect day on yesterday, so that's why it's removed. So now it's there, and you can continue doing your homework. Okay, what else? Well, if you have a problem like this, just send me a WhatsApp or an email right away. Don't wait until class time to tell me if you have any problem. We can fix it right away. Okay, anything else? Okay, today, inshallah, we will be solving mixed problems on different chapters. And you realize that things get interconnected, mixed together. And we will make that link between the analysis, what we had last time for the past 10 weeks or 9 weeks, and the design, which we will start inshallah on Monday. So today we'll be solving a problem to find the takeoff distance S. This is mainly a question on chapter 6. Problem on finding the induced drag coefficient K. Now that's an aerodynamic thing in chapter 2, but we will realize that we will need something from chapter 5 as well in order to solve it. And finally, a problem on finding the wing loading. We had the wing loading in chapters 5 and 6. So let's start our first problem. The problem reads, the shown Boeing 727 aircraft has the following characteristics. The Boeing 727 is a short to medium range transport that was developed back in the 1960s. Very efficient, relatively short runways for takeoff and landing. Very economical aircraft. It lived for more than 40 years. Actually, it's still flying right now, even if when it got older, for passenger regulations, what they did, they just converted it into a cargo. They took the seats on the top and make it carry cargo. So it's a very efficient workhorse in the aviation industry. That aircraft has some characteristics that we are given here. So we are given the maximum weight of the aircraft, the stall speed in knots and in feet per second. And I hope now you know the conversion factor. Wing area is given, the takeoff flap angle. That means when the aircraft is taking off, the flaps are deflected downward by 20 degrees. The wing sweep angle of the leading edge is 32 degrees. It's swept backward. The maximum lift to drag ratio 19, zero lift drag coefficient knots 0.17. Average thrust during the takeoff is 8,786 pounds. And it's required to determine the obstacle clearance takeoff distance. That means the required takeoff distance of the aircraft to clear an obstacle of a height of 35 feet. Or 50, depending on the regulation. So here we're talking 35 feet of this aircraft. The question is, what is the takeoff distance? So in order to solve the problem, I will go and check the equations that I have on the takeoff distance. I will find that the full takeoff distance is divided into two pieces. piece on the ground and piece on the air. We had an equation for this last time. The piece in the ground depends mainly on the thrust to weight ratio and the speeds, and the ratio on the air will be determined by the arc by which the aircraft will climb. So I need to calculate both component SG and SA. Now looking at SG, we mentioned last time there is a long procedure to calculate SG that includes the lift and drag on the aircraft. Talk about a couple of pages, and then at the end the textbook provided a more simple equation that provides the distance with an error of about 1%. That's very good for a single equation. So we will use this equation in order to determine the ground roll, the area when the aircraft is running on the ground. It's a function of the wing loading, W/S, thrust to weight ratio, CLmax of takeoff, as well as the density of the air. So looking at what we have the weight given, the area given, the thrust given, the density of course is at sea level. The only thing that we are not given is the CLmax of the aircraft. If you look at it here, it's not there. Okay. Now you can, if you want, divide the weight by 1/2 rho S and use the stall speed to get CLmax, but that will be the CLmax if the aircraft is taking off at stall speed, which it doesn't take off at stall speed. So one way to find the CLmax is to say, okay, this is during takeoff, and I know during takeoff the aircraft is using flaps. We are given the flap deflection. So we had a table that would tell me for each type of flap what would be the CLmax of that flap. It's not giving me directly the CLmax, it's giving me CLmax over cosine the sweep angle of the wing. But for a Fowler flap, triple slotted flap, it's giving me a range of CLmax during takeoff and landing. Since I am in takeoff, I can use any value in that range in order to determine that. Okay, so for 20 degrees, triple slotted Fowler flap, which is the flap of this aircraft, I know that the CLmax is between 2.4 and 2.7. You can assume, and you will hear that word so many times from now on, you can assume any reasonable value in that range. 2.4, 2.5, 2.6. Here I used 2.7. So taking the 2.7, and we know the sweep angle of the aircraft, the lambda is 32 degrees, I can get the CLmax. So CLmax will be 2.7 cosine 32 degrees. Turns out to be 2.28. Okay. So during takeoff, this wing will have a CL of 2.28. Okay. Now that's assumption that we did in here. Okay. Any question in this part? So we will start deviating a little bit from the sort of problems where you have everything given, you all have to do is to substitute. Okay? Because not all the information is usually known when we do design. So if I have CLmax, now I have everything to get the ground roll distance. I will put CLmax, I will put the thrusts given in the problem, weight given, area given. This will give me, here is the weight and the area, here is the thrust and the weight. This will give me SG of 6,100 feet. Okay, so that's for the area on the ground, the ground roll. The next part will be the part when the aircraft is leaving the earth and just leaving the ground and going up to an altitude of 35 feet. What would be that distance? Now that distance can be obtained by r sine theta. So I need r and theta. Theta can be determined from that distance divided by the radius and inverse cosine. But in order to get that distance, I have to get r minus h. So the starting point is r. So r here, we have the equation of that from chapter 6. The radius is a function only of the stall speed. Since we have the stall speed, I know the radius, 5,000. 131 feet. Then I'm using the radius and the h in order to get the theta. So theta is 6 degrees. And from the theta and the r, I can determine the horizontal distance SAR sine theta to be 625 feet. If this distance 625 plus 6111, so the total distance is 6,700 feet. That's the total distance from the release of the throttle start acceleration up to a height of 35 feet. Okay. Any questions? So you realize that we start doing some assumptions here. You realize that we have been going between chapters 5, 6, and sometimes 2 in order to find the parameter for a single problem. Okay. If you don't have questions, then I'm moving on to the second problem. Again, for the same aircraft where we know the specifications, nothing has changed in the specifications. We are required to find the drag due to lift coefficient, the K of this aircraft, which appears in the drag polar. So the drag polar, which is CD naught plus KCL square, we need that K. Okay. Given the information of the aircraft. Now, nothing helps me here in the K because usually you used to get K from the CD alpha curve or CL curve of the aircraft. You would read that. But now we want to calculate it from the performance of the aircraft. Okay, so in aerial problems in chapter 5, you are given C and K and find some performance, find the maximum speed, find the maximum range, whatever. But here we are going the other way around. Knowing the performance, what would be K that's required? So the performance characteristic that relates to K, one of them is the L over D max, and it is the one that's given in here. We know maximum L over D is 19. But we know that L over D is also 1 over 4 CD naught K. You already have used this equation, actually use the inverse of this equation. Instead of 1 over, you used 4 CD naught K. Instead L over D, you used thrust over weight, because thrust over weight is D over L. And you use this in the quiz, the midterm. So L over D 19. CD not given, the only unknown here is K, so I can determine K here, and it will be 0.04. Okay. Now, why are we having this example? It's just like the what you had in the exam, put K CD not get LD, because in design you will go the other way around. We will not start from non-drag polar. We will start from requirements. When we do design, it tells you, I need to satisfy these requirements. Go ahead and find me an airfoil and a wing that will give me this requirement. So this is one way of doing that, to start finding the drag coefficient, the parasite drag coefficient CD naught, or the induced drag coefficient K. Okay. The third problem looks at something that's done in design, which is finding an alternative for the initial design. That means people start doing some design and then they will look, what if we increase this value or decrease this value, how things are going to be changed. So let's say we have an alternative to the design of this aircraft, and it's required that the landing distance be only 4,900 feet. You realize that the takeoff distance was about 6,000 something. The landing distance is required to be reduced to 4,900 feet. And for this, the assumed stall speed or the used stall speed will be increased to 99 knots. Everything else will remain the same. The weights, the wing area, everything else. Now, why would a designer do this? Typically, we do not change the stall speed because it's specified by the regulations. Regulations tell you you cannot have a stall speed more than a certain number of knots. For transport aircraft, it would be 100 knots. Since we already used 91 before, you see the stall speed that we had before was 91 knots. We can, if we want, increase them a little bit and see what effect would that have on performance. So what is that? Yes. So here the stall speed has been increased to 99 knots. And we want to see if we want to make the landing distance 4,900, what would be the wing loading? And the question of asking about wing loading, it is as if we are asking about the wing area. Because you see the wing loading relate W over S. If you fix W and you change the wing loading, that means you have changed the area of the wing. So that's the question. What is W over S to satisfy this landing requirement? Okay. So we need to relate somehow W over S and the landing. So I need to look at the landing distance. Chapter 6. What did we do in the landing? We said, and we solved the problem on this last time, the landing consists of 4 parts. Part number 1, aircraft is going down at a straight line, final approach. Part number 2, when the airplane reaches a height called the flare height, nose will start coming up, rotation will start, slowing down will start. I will start here with the speed, the rotation, the flare speed will decrease and become the landing speed. And once the airplane touches down, it will start rolling for about 3 seconds on the ground, and it will cover some distance in these 3 seconds. And then the aircraft's brakes will be deployed at this point. It will slow down until it comes to a stop. So I have part 1, 2, 3, 4. We need to find the total distance, but the total distance is given. So I need to use the value that's given in order to determine W over S. Where is W over S in all these parts? If you have studied last time, or if you have the textbook and look at this figure, you will find that the horizontal distance in the first part is not a function of W over S. It's a function only of the speed of the aircraft. In the second part also doesn't depend. It depends on the wing loading here and here. Only these 2 parts depend on the wing loading. So in order to solve the problem, we will calculate the horizontal distances SA and S flare, and I will subtract him from the total distance to give me the distance on the ground, and I will use it in order to get the wing loading. Okay. So let's do this. In order to determine both the distances, I need to determine the flare height. And the flare height is determined from the radius as well as the theta in here. Okay, so for this, I have to start with the radius. And we found last time the radius is a function only of the speed at which the aircraft will start rotating the nose up, which is the flare speed VF. So the radius from the flare speed gives me about, what is that? 6,500 feet. How did I do this? I need to use a flare speed. Now, we mentioned last time that the aircraft will start slowing down until it reaches 1.23 vstall, and then it will slow more to 1.15. So the flare speed is 1.23 vstall. Since we have the stall speed, I know the flare speed. So that would be the flare speed. Since we know, and it's not mentioned in the problem, since we know that transport aircraft typically approach the runway with a descent angle of 3 degrees, or the approach angle is 3 degrees, then we will use the angle of 3. Okay. So using the 3 degrees and using the flare speed, I know now the radius. In here, 6,500. If I know the radius and I take it, where is that? If I know the radius in here, if this is 3 degrees, This is 3 degrees. I know the radius. I take cosine 3 degrees times the radius. That's giving me that height. If I subtract it from the radius, that will be the flare height. Now, I'm not going to derive this every time. All I have to do is to use the equation. The flare height is r minus r cosine theta. So turns out to be about 8.5 feet. About less than 3 meters above the ground, the nose will turn up. Knowing the flare height, HF, I can subtract it from the 50, and I will use it with the 3 degrees to get the horizontal distance. Again, I don't have to derive it every time. The equation is there. From the flare height and the theta give me the horizontal distance, 700 feet, 790. And what about the flare distance? The second one, SF, it's r times theta, sine theta. R times sine theta will give me that horizontal distance. So it's r sine theta, about 300 feet. You see these two distances, it's when the aircraft is on the in the air. Remember when we talked last time, we said this distance for transport aircraft is about what? How many feet? From the obstacle all the way to touchdown. About how many feet?
30 to 50.
No, 30 to 50, that's the obstacle. The 50, this height could be 35 or 50 depending on the aircraft. But the horizontal distance for the aircraft from the moment it clears the obstacle until it touches down, we said this distance would be around 1,100 feet. We are talking about 350 meters. Okay, so you see, even here in this problem, if you add the numbers, turns out to be about 1,100 something. Almost the same. Almost. Because why is that? Because it depends mainly on the speed and on the angle, which is almost the same for all transport aircraft. Think of this distance as the distance, roughly, that you have from the wall of the airport until the point when the aircraft touches down. When you are in the aircraft and it's landing, you cross over the fence around the airport, and then the aircraft will continue to fly a little bit, then will rotate, and then will touch down. Distance is about 350 meters, about 1,100 pounds, feet, roughly. Okay, so that's the 1,100. What about the other two distances? Well, we have an equation for these ones. The sum of these is called the ground roll. One free roll, no brakes, and the other one with the brakes. So we have the one term for no brakes, the other one with the brakes. May I remind you in here that J was the ratio of the speed. That means the landing speed is J times the stall. So it's 1.15 times the stall. So J times the stall. You see this route, that's the stall speed. This route. So J times the route is 1.15 V stall. If this is the speed, multiplying it by time n gives me the distance. So speed times time is equal to distance. So n here is 3 seconds. It's the time of the aircraft rolling on the ground without the brakes being deployed. So this is the first part, and that's the second part. When the brakes are being deployed, it will depend, of course, on the coefficient of friction due to the braking, 0.4, which is the mu here. So what do you think this distance is going to be? Can you give me a value on this distance? How are you gonna, do I know SG at this point? Do I know this distance, SG, the value of the ground roll? Do we know this value now?
Yes.
Yes, it's the 4,900, that's the total here, minus the 790 minus the 343. So I know this one. If I find the other parameters here, the only unknown should be the wing loading that's required in the problem. So W over S should be unknown in here. So let's start. What do we have? J is 1.15, N is 3 seconds, density at sea level, mu coefficient friction 0.4, which is typical. CL max, do we have CL max?
No. Or was it? No, we don't have it.
Let me go back. Do we have CLmax? Remember in takeoff, we calculated CLmax from this table, right? And there was another column for the landing. So I can calculate CLmax from the same table, but for the landing condition. So I will do this in here, in my problem. I will calculate the CLmax from the landing condition. You see, again, it's Fowler flap, triple slotted landing. Now the deflection is 40 degrees. I can use a CLmax over cosine of between 3.2 and 3.5 rather than 2.4 to 2.7. It's higher now. So if I take the value multiplied by cosine the sweep angle, 32 degrees, it will be the 2.61. That's CLmax that we are using here. So I'm substituting for CLmax in here as 2.61 obtained for the landing condition. Don't use the takeoff values because they have changed.
Which is any number between 3.2 3.5?
Yes. Again, we are making assumption. Why are we making assumption? Because you see this table, it's not only for this particular aircraft or this particular flap, because if we have all the information of the aircraft, then there is no need to design it. This table tells me if you use a Fowler flap, which is triple slotted, we have a history of aircraft that used it, and their CLmax ranged between 3.2 and 3.5. So this, think of this table as the experience table. It is the table that a designer would have on the top of his mind by seeing similar aircraft or by designing other aircraft. So yes, between 3.2 and 3.5. Okay, so this 2.6 here, I think it was taken at 3.3. If I remember correctly, 3.3. You can take any value. And of course, that means if you are solving a problem in a quiz or an exam or a homework, you might get a different answer than the answer that's provided by the system. And that's why we have a range in there. So we are going to make some, this is what we call a reasonable assumption here. And it's not the only one that we will do today. We're going to make another one in a few moments. So putting the values of density, the CLmax, the coefficient of friction, J and N, the only unknown is the wing loading, W over S. And you see, we didn't ask for what's the weight or what's the wing area. It's the wing loading together that affects, because maybe if I don't change the weight, I need a bigger wing or a smaller wing in order to achieve the requirement. So with the wing loading, substituting all of these here, we know SG as the total landing minus the two parts in the air, turns out to be 3,775. I'm going to put it here. And if I do so, the only thing that we have unknown in the problem is the W over S. See W over S here and here. It's the only unknown. Here we have a coefficient multiplied by W over S is 16. Here we have a coefficient multiplied by the root is 61. And here's the 3,700. In order to solve this equation, of course, you will plug it in your calculator, but remember in your calculator, the unknown would not be W over S, it's the root here, right? So you can think of this as a quadratic equation where I have free term, coefficient times X plus coefficient times X squared. This is a quadratic equation that will get two solutions. So if you put it in your calculator, you will get two solutions for this. One of them would be 13 point something. That means the root here is 13, making W over S 178. Okay, and the other root, of course, will be fictitious. So please don't write everything that comes out of your calculator, because it will probably be a negative number. And W over S negative doesn't make any sense. Okay. So knowing the roots, we have the wing loading of about 178.15. If the weight of the aircraft remains the same, then the new wing that is needed to make this aircraft land in a shorter distance will be the weight divided by the 178. Okay. So that will be the new wing that's required for this case. Any questions?
Doctor,
Yes.
the time n equal to 3.
Yes.
How did
What's
we
the time? That's 3. Yes.
How did we
This-
know it?
No, again, this is not. How did we know the 3 degrees?
And,
How did we know the 35? This is agreed upon by convention that average height of an obstacle around airports, let's take them 35. Let's agree on something. So 35 to 50. So that's by agreement. In here, 3 degrees, how did we get these? This is the reasonable, comfortable one for passengers, for example. You don't want the aircraft, although it can come down at an angle of 6 degrees, sometimes 7 degrees. That would be too much. You will be scared as a passenger for an aircraft going down like this. Okay. What about here? The 3 seconds once the aircraft starts touching down until it reaches here. Now, that's common for the industry. If the pilot hits the brakes too early, then the aircraft will be too fast and the tires will be torn and worn more frequently. So they will need to replace the tires more frequently. So he had to slow down a little bit, let the drag slow him down slightly before he hits the brakes. But on the other hand, if he keeps rolling for 5, 6, 10, 20 seconds before, of course the aircraft will slow down a little bit. And then he can use the brakes and the tires will be fine. But in this case, what would be the problem?
more distance.
More distance, which is not a good thing. So it has agreed that like typical reasonable time for the aircraft to roll on the ground before hitting the brakes is the time when its speed comes down from 1.15 VSTOL to roughly VSTOL. It's very close to the VSTOL. And this time is about 3 seconds. So once the aircraft touch down, you can count 1, 2, 3, and then you will feel the brakes being deployed. Okay, roughly. I'm not saying that's the exactly 3 seconds, but in design we count on these 3 seconds. Okay? It could be 2.5 seconds. It could be 2 seconds. It could be 3.5, depending on the runway condition as well. If you have a wet runway, the pilot will not deploy the brakes before maybe 4 or 5 seconds until the aircraft slows down a little bit. Okay, does this answer your question?
Yes, thank you, Doctor.
Okay, so we have, that's one assumption that we did. Another assumption that I used and no one corrected me on this, I told you, you come here, you take the CL max and multiply by cosine 32, you will get 2.61. I want you to keep the habit of having a calculator handy, and whenever we do something like this, you go and check me on the numbers, because you will not get 2.61. Okay, there is something else hidden from this point to this point. Now, in tables like this, or in curves of CL versus alpha, the ones that we had in chapter 2 and you had difficulty reading from, or in drag polars, all of these are made on airfoils, measured in wind tunnels, for example. And airfoils are 2-dimensional wings. They have no span, or on the other, we can say they have infinite span. So the span doesn't play an effect. So whatever value we read here is for 2-dimensional flaps. That means if the wing has finite, that means it has a span, the CL max will be decreased a little bit because of the 3D effect. It's not going to be exactly as you read from the charts or the tables. And it has been agreed based on experiments, based on experience, that this decrease from the 2G values which we have in tables and charts, to the 3D, which we need in the equation, because the equation doesn't know 2D. It says CL max of the wing. The ratio from here to here is about 0.9. We lose 10% of the 2D CL when we get to the 3D. So if you take the 3.3, for example, or 3.2, and multiplied by cosine 32 degrees and then by 0.9, you will get the 2.61. Of course, you can ignore that 0.9 and you can just use it, but your results of CL max will be overestimated. So this value here will be higher than expected or higher than actual, which will give you a slightly different incorrect value of W over S. Again, that's a reasonable assumption that we do. Okay. So you heard me talk about assumptions 3 times today. You will hear this more as we start chapter 8, doing the design. You realized here that we went through equations from chapters 2, 5, and 6 in the same problem. So that's what I want to leave you with today, that when we start to do design, we realize that all sciences are connected. Equations of motion, kinematics, propulsion, aerodynamics, structure, sometimes costs, convenience, environmental science, all these are going to be related together. Also, the equations in one chapter might need equations from the others to find parameters needed. So please don't think by the mentality of a regular course and a regular textbook. That means don't look at a problem from now on. After the homework they are doing in chapter 6, when we go to 7 and 8, don't look at it and say, okay, this is a problem on chapter 2 or chapter 5. No, it will not work this way. You must have that global scope when you look at the problem, when you approach design. You will use whatever tools in your capability, whatever information, whatever equations you have in order to find the unknowns. And sometimes you will not have enough, you will make assumptions, you can make a small test, you can think, you can look at similar aircraft and so on. And you will do these assumptions, as you have seen, we have done them like 3 times today. 2 of them actually are new assumptions. The one of them was we had before, the 3 seconds we had before. Okay, any questions? Okay, so where are we going from here? Inshallah, on Monday, when you submit your homework on chapter 6, it's one problem for chapter 5 and one problem on chapter 6. We're going to introduce the design process. That means we're going to lay out a roadmap that we will follow in the remainder of the semester. Because as you see, 2, 5, and 6 are all related. 4, of course, is the equation as well. So where to start and how to proceed from the requirements in order to develop an aircraft that's not there. Remember, these problems that we had today, we had the aircraft, we knew how it looked like, we know some information about it. But what if I want to design an aircraft that the only thing I know of is, let's say, nothing that you see in this page. Okay. I only know that it needs to carry a certain number of people, go for a certain distance, have a certain takeoff distance, and that's it. I know nothing. Okay. I don't know the shape and none of these. So where to start in all this mess in order to come and develop this information? So we will have that roadmap ready on Monday, inshallah. Starting Wednesday, we will start chapter 8 by using or implementing this roadmap in the design of a propeller aircraft. It will take us about 3.5 weeks, 3 to 4 weeks in order to finish it. And in the process, you will be following us with your team in the design project. So we'll go with the roadmap and you will do the same with your design project in a separate, different aircraft. In the last couple of weeks, we're going to have the same procedure for jet aircraft, and we're going to go quickly over it because it's basically the same procedure, but for different aircraft. And you will be finalizing your design projects, and you will submit in week 15, inshallah, and you are going to make a presentation. So we need to finalize on the teams by Monday. I need 3. Oh, no, I still have one more thing to say. How many of you have taken AE210? Can you raise a hand? I'm sorry, ME210. Can you raise your hand, ME210? SolidWorks. Graphics. I hope many. Because if not, then we are in trouble. No one knows how to use SolidWorks. Now that's strange.
Yes, we know, Doctor.
Can you raise a hand? I need to know something here. Can everyone who have taken ME210 raise his hand? Only Marwan?
We
Or
raised
currently
our hand.
taking?
There are
Me,
Either have taken or
I
currently taking?
I'm raising my hand, Doctor. Doesn't show.
No. Okay. Who's this? Mushari?
Shari. Yes.
Mushari.
There
Okay.
are 19 people, Doctor, who raised their hand.
There are what?
19 people who raised their hand.
Oh, really?
You
I
have
have only
to
six. How
check
come?
from the meeting participant.
Oh, can you? Oh, yeah, it is in the participants, but in the participants I have only 4.
Yeah, me too. I can see 4 all.
I can see only 4, so I'm surprised. How did you know that there are 19 who raised their hands?
Yeah, Doctor, we are 20. 19 now.
Oh, good. That's good. Okay, I don't need. Okay, yeah. Now I can see them. I took this guy. Why I'm saying this, since we have so many of you, I want. Well, that's not going to be a problem. Typically, I don't want all the people who know SolidWorks gathered in one team, because now I'm going to have one drawing and the other 2, 3, or 4 teams will not be able to do. But since we have so many of you, that should not be a problem. So I need in every team at least 2 to 3 students who know how to do SolidWorks, so that we have a drawing at the end. So I'm leaving the team formation up to you. Okay, thank you. You can lower your hand now. Thanks. I need by Monday 4 to 5. No, 5 to 6 of you to form teams. The team should be somewhere between 6 and 8. 6 is fine, 7 is fine, 8 is fine. So, and I need, of course, everyone on this course to be in one of these teams. Okay, and I'm leaving it up to you. But if you fail to organize yourself in a team, then I will go and I'm going to arrange it by the order in the course. I will tell you, okay, it's like 5 teams, first 8, then the second 8, then the third 8, and so on. But I don't like that. I want you to work with people whom you are familiar with. So organize yourself in, I would say 5 teams. 5 teams. Okay, we have 39 students, so 5 teams should be okay. So by Monday, I need 5 emails from 5 of you saying, okay, I am the team leader. Now, make no mistake, the team leader is not the one who's going to get the highest grade in the team. That's not the point. It's the one who will be contacting me regarding his team, and I will be contacting him regarding feedback to the team. So I need 5 emails from 5 team leaders. There is no grade bonus comes with a team leader, so don't put your hopes on this. Telling me in each email I need a list of the students on this team. And accordingly, I will make groups in Blackboard for your team, so that when you submit, you will submit 1 work per team. You will submit twice. You will submit what's called a progress, maybe like after 3 weeks, and then a final report, and then you will make a presentation. Okay. You will put all your work in the group folder on Blackboard so that I can check it, give you a feedback. If you make mistakes, I correct you. Think of a platform that would be good for your team to work with. Maybe you guys want to work with Excel or MATLAB rather than using handcalcs. It will save you a lot of time if you do that. But if you want to go with handcalc, that's okay. You will pay the price. You will waste some time. Okay. So form the teams by Monday. Send me, I need 5 emails for 5 teams. And I'm going to present the project inshallah on Wednesday, and we will go hand in hand. I will be in the lecture describing the design process, and you will be doing the same with your team. Okay, Shabab? Now, is this raised hand now, do you have questions or you still didn't lower the hands? Any questions? Okay, so if we don't have questions, then inshallah